Hello everyone, I'm Sebastian Marino and I'm very excited today to be giving this lecture to the Severo Ochoa School. I'm a research fellow at the University of Cambridge working on debris disks, and today I wanted to basically share a bit with you what has been going on for the last years on researching debris disks. And for that I thought we could divide this lecture starting with an introduction, so the most basic kind of terms are clear, that you understand when people talk about different things related to debris disks. Then I would like to tell you about what we have learned over the last 4 years, more or less, about the structure of these disks, how the dust is distributed, and also about the gas component in these disks, which has been a very hot topic over the last years. Okay, so let's start with some fundamentals. It's a good idea to start from the solar system perspective because many of the terms we use are related to the solar system science. Okay, so we know that the solar system is not made only of planets, right? It also contains smaller bodies. This can be in the form of dust, like for example the Zodiacal cloud, which can be seen from Earth with your own eyes as a kind of halo along the ecliptic. And also, we can see with telescopes actually individual planetesimals. So these are asteroids or comets that could be in the asteroid belt or in the Kuiper belt or just around being scattered by planets. So these small bodies are a natural product of planet formation, and together they constitute the solar system debris disk. How these bodies form? Well, it's a very complex question actually. But just to be in a common framework, let me kind of try to draw this common picture. So when a star is formed, after about 1 mega year, we know that it should be surrounded by a gas-rich protoplanetary disk that is very massive, contains gas and dust, and the gas mass or densities are a factor about 100 compared to the dust. By 1 to 5 mega years, the dust should grow and it usually should form planetesimals and planets. And those planets, perhaps if massive enough, could carve gaps in the distribution of gas and dust. By 10 mega years, we know the disk should disperse and we're left with things like planets, but also with planetesimals. And these planetesimals might be clustered in belts that are analogous to the Kuiper belt or the asteroid belt in the solar system. So how can we detect this debris component? The easiest way is actually to look for dust around other systems. And for that, we can look at infrared excess, okay, generally at wavelengths greater than 10 microns. So if we look at another system, we might be able to detect this extra component in the spectral energy distribution of a system. And from this extra component, we can actually start learning a lot of unique and fundamental information of this debris component. So there are two basic properties we can start learning about. The first one is called the fractional luminosity. And as its name says, it's basically the ratio between the luminosity of this debris component, so the dust emission, over this the stellar component, so the stellar luminosity. And this ratio must be equal to actually the fraction of the energy irradiated by the star that is captured by the dust, so absorbed by the dust. So from simply geometry, that basically fraction must be equal to the cross-sectional area of the dust divided by 4 pi r squared, which is the area of the sphere. Okay, r here is the distance between the star and the dust. So we know, or from this quantity, we can learn something about these two quantities, although it's degenerate, right? But from the peak of emission of the dust emission, we can know what's the temperature of the dust, right? And because the dust should be in thermal equilibrium, we know that the temperature of the dust and the luminosity of the star tells us what's actually the radius and what distance this dust is. So the further away it is, the colder it should be, and the closer to a star, the warmer it will be. And from this kind of studies, right, just by looking at hundreds of stars, we have learned that about 30% of AFGK stars have a lot of dust around them and actually have dust levels that are greater than 10 times the Kuiper belt levels. So we know that it's possible that all stars actually have belts of planetesimals and dust like the Kuiper belt, but only 30% are massive enough that we can detect them today. But in the future, this number could change, okay? So where is this dust originating from, right? Is it just a remnant of the protoplanetary disk? Well, the answer is no. And the reason for this is that if we compute the lifetime of those grains, we find that the lifetimes are much shorter than the age of the systems. And this is because there are different processes removing the dust, such as radiation pressure, pointing Robertson drag, which causes dust grains to spiral inwards towards the star, and collisions, which naturally will just break dust grains. So they will get smaller and smaller and smaller until radiation pressure, which acts more strongly on small grains, would be removed from the system. Okay? So this kind of was realized in 1993 and was kind of the start a bit of the science on the debris disks. Okay, so how is dust being replenished then? Because to see it today, it means that it must have been produced recently. So what we think is going on is that there are larger things, kilometer in size, that we call planetesimals, that are colliding with each other, and when they collide, they produce dust. Okay, this process can be modeled, and we tend to call it collisional cascade. So in this figure that you see on the right, you see what's the size distribution and how it will evolve with time. The x-axis is the diameter of bodies, and the y-axis is how much mass there is in bodies of a given diameter. And what you can see is that with time, mass from the top, the size distribution from the large things, will move down with time, replenishing the smaller things. So in general, with time, the total mass of the disk will go down with time, but the mass in the small things will have a level that is not going to drop as fast as it would drop if these large things were not there. Okay, so what happens once you reach the bottom of the collision cascade? This process is a bit complicated, but can be understood very simply with the following diagram. Okay, the key thing to understand here is that there is not only gravity in the system, so solids not only feel the gravitational force from the star, but they also feel some radiation pressure. Okay, and the ratio between the gravitational force and radiation pressure, okay, we call it beta. So this is gravitation, the radiation force over gravitational force. And this ratio is roughly proportional to 1 over the size of a given body. So for large things, beta is very, very small, and that means that those bodies are, the dynamics of those bodies are simply controlled by gravity. Okay. So now imagine you have a big planetesimal on a circular orbit around a star. Beta is much, much lower than 1, so the orbit of that planetesimal can be simply modeled with gravity. Now imagine dust is released from that planetesimal at the same velocity the planetesimal is going. Okay, so that dust grain will actually feel some radiation pressure. Okay, so beta for that dust grain might be not much smaller than 1, and therefore the central force that that dust grain will feel will be weaker. Okay, and because it's feeling a weaker central force, it basically has too much angular momentum to stay on a circular orbit. That means that that dust grain will be put on an eccentric orbit once released from the planetesimal. Now you can imagine, or you can see it coming, that if beta is even larger, then that dust grain might be placed on an orbit that is actually unbound. So for a beta of 0.5, a dust grain that is released from an initially circular orbit will be put on a parabolic orbit. And if beta is even larger, the orbit will be hyperbolic and it will exit the system very fast. So you can see that as mass then goes down this collisional cascade, once it reaches a size of about 1 micron for a solar type star, it will have a beta value of 0.5. And once that happens, that dust grain will exit the system. So mass is being lost away from the system via radiation pressure. We know this process is going on because we can actually see the dust mass in systems to go down with age. We cannot see it for a singular system, but if we look at how much dust there is among many systems, like shown in this figure, we can see that for systems younger than 10 megayears, dust levels are very high. Systems have a lot of mass in dust in protoplanetary disks. Beyond 10 megayears, systems have less dust, and those dust levels seem to decrease with age. Okay. So how do disks look like actually? So, well, that will depend on the wavelength at which we look at them. For example, we can look at them at optical wavelengths where we're not sensitive to the thermal emission from the dust. As you can see from here, it should be very low. But we can see actually light coming from the star that is being scattered by the dust. Okay? And that dust is actually very small. It's dust that is dominating the cross-sectional area of the disk. That small dust is subject to radiation pressure, so we expect the dust to be on elliptical orbits, so forming a kind of halo. We can also look at disks directly in thermal emission, so for example with Herschel or with ALMA. Okay, so the important thing here to understand is that the longer wavelength we observe these disks at, the more sensitive we will be to larger grains. And that's very important because, as I told you before, the larger a solid is, the smaller will be the effects of radiation pressure. So the big grains traced by ALMA will not feel a strong radiation force as the small grains that are traced by a sphere image, for example. So that means that these big grains will stick around more or less where they were released, versus small grains being all over the place, basically. So this comparison of an HST and ALMA image of the same system is showing that. So small grains are blown out by radiation pressure and are shown in blue, and in red you can see what ALMA actually sees for this system. So they're all like confined to a narrow ring where dust is being produced. So this is telling us that actually the planetesimals in this system are confined to a narrow ring, while the small grains are all over the place, being pushed away by radiation pressure. Okay, so just to summarize these concepts, we know that planetary systems are not only composed of planets. There are also asteroid or Kuiper belt analogues that are formed also in protoplanetary disks. And this special component that we call exoKuiper belts, so Kuiper belt analogues belts, distances greater than 10 AU, are actually very common, and they are found at least around 30% of AFGK stars. So why debris disks are important? Why is all this relevant, right? Well, there are different reasons, or different answers to that. My personal opinion is that debris disks are fundamental for understanding the architecture of planetary systems. Okay, and this is because of the following. If you look at how much do we know about exoplanets, if we look at where are the exoplanets that we are finding, the thousands of exoplanets we are finding today, you can see in this figure that is planet mass versus semi-major axis that they're distributed right at basically small radii or a large radii but with very high masses. We have a huge gap in our understanding of these outer regions where planets like Neptune or Uranus or even Saturn are. Okay, luckily, this is the same space that exoKuiper belts tend to occupy. So by looking at exoKuiper belts and their structure, we get a unique window into the outer regions, and we can use this to infer the presence of planets. Okay, and this is why studying the structure of debris disks, which is the next thing I want to discuss, is so important. Okay, let's talk about disk structure. As well as before, it's a good idea to start by looking at the asteroid belt and how it is shaped by Jupiter. If we look at the eccentricity versus semi-major axis distribution of asteroids on the left, we can see that the presence of Jupiter here, at around 5 EU, creates gaps in the distribution of asteroids, right? So these vertical gaps corresponds to mean motion resonances with Jupiter, and are regions that are unstable. Basically, their orbits along these dashed lines will be unstable due to the presence of Jupiter. So if we were able to do a map like this for a debris disk around another star, we could actually infer that there should be a planet over here. However, this is eccentricity versus semi-major axis distribution. And this is not something that we can directly see in another system. But actually what we will see will be something like this figure over here, where we have X versus Y plot. So this is a surface density, basically, figure. This is kind of what an image would look like if we were to take a picture of the asteroid belt from above. So as you can see, we don't see any of these gaps. But what we can see actually is that there are two clouds here and here that corresponds to Trojans. So these particles here and here are at the same semi-major axis as Jupiter, and they are on stable orbits. So if we were to look at another system and find these kind of clouds, we would know that there should be a planet more or less over here that has trapped these Trojan particles over there. Okay. So another thing that we can look at is the Kuiper belt. Okay, the Kuiper belt, similarly, similar to the asteroid belt, is also shaped by the presence of Neptune in this case. So if we look at, again, the eccentricity versus semi-major axis distribution, we can see that it's full of structure. Okay, this figure over here is made of basically a synthetic population of Kuiper belt objects that fits very well the data. So Neptune, the semi-major axis of Neptune is more or less over here. We can see that it's already truncating the inner edge of the Kuiper belt. Then we have a population that's kind of dominant over here between, let's say, 40 and 45 AU or 50 AU. And then there are extra populations like these ones that show in vertical lines that are present at specific resonances. Okay, so this is a resonant population. And then we have this other population with very high eccentricities on large semi-major axis, which forms a scattered disk. So this population over here have pericenters that go all the way down over here. So particles over here will have close encounters with Neptune and are being scattered. So again, for an extrasolar system, we wouldn't be able to see this, okay? But what we will see, more or less, is something like on the figure on the right. So this is the surface density, okay, that you obtain when taking the orbits of these particles. So we have a strong peak around 45 or 50 AU that corresponds to particles over here, okay, and also to the pericenter of the particles in this scattered population. But we also have this very extended component that is the scattered disk. So all these particles have a high eccentricity. And if we were to look at another system and find such kind of population with a very specific slope like that one, we could infer that perhaps there's a planet located at the inner edge of this disk that has scattered all that material. Okay, how much material is in this scattered population versus this population that peaks over here could tell us about the history of this belt and the planet, in a similar way as the Kuiper belt tell us some of the history of Neptune and how it migrated in the past. So another thing that we could potentially observe in another system is basically a distribution of bodies that is asymmetric, that is not axisymmetric. An example of this is the proposed Planet 9 in the solar system, which was basically proposed to explain that the orbits of Kuiper belt objects, some Kuiper belt objects, seems to be clustered. So these objects are on eccentric orbits, and the pericenter or apocenter of those orbits doesn't follow just a random distribution. Okay, so they seem to be clustered towards a particular direction, and perhaps the only way to achieve that, right, as proposed by the authors in 2016, was with the presence of an additional planet. So if in another system we see the debris disk looks to be asymmetric or eccentric, okay, it might mean that there could be a planet forcing this kind of clustering towards a particular direction. So these kind of things that we have seen in the solar system have motivated a large number of studies thinking about different scenarios and what we could see in other systems. For example, inspired by the solar system structure, Sebastian and Weiger 2016 showed that if you had a planet on a slightly eccentric orbit just interior to a disk, it could create a kind of like croissant gap shape that you see here. And this could potentially be observed in a system. Also explored by Pierce and Wyatt, they thought about how would a disk look like if it was interacting with a planet on an eccentric orbit. So this is basically very similar to the case of Planet 9. And the answer is that, as I told you before, the eccentricity or the orbits of those particles interacting with this planet will kind of be forced. The orbits will be forced to high eccentricity orbits, and the direction of those orbits will be forced to be towards a specific direction that is aligned with the orbit of the planet. So in this case, the star is in the center. The dashed line represents the original kind of extension of the disk, and in color you see the final surface density that you get after a few mega years of interaction with this planet on an eccentric orbit. Another case studied by Nesvold in 2013, in a similar experiment, they showed that a planet on an eccentric orbit could also produce, right, this eccentric ring of planetesimals and dust that in this case is very narrow due to collisions damping a bit the eccentricity of particles and slowly converging towards a case where they are all perfectly aligned with the orbit of the planet. Finally, we could have a case where a planet has migrated through a disk, like for example Neptune and the Kuiper belt. And while doing so, you have that planetesimals will be trapped in resonances. So these resonances, as a planet migrates, they also move. And while they move, they can trap particles in them. And when doing so, you get these resonant populations. And actually, those resonant populations can form some coherent structure that can create clumps, like in this case. And these structure that can be clumpy for planetesimals, here with beta very, very small, can actually have different shapes depending on beta. So depending on the wavelength at which we look at a given system, we could see a structure that looks like clumpy, for example, for large grains, and just axisymmetric for small grains, or even forming some spirals for very small grains that are unbound in the system. So have we observed anything like this in disks? The answer is we're very close to it, or we have already done so. So one specific case is the famous system HR 8799 with 4 planets, 4 giant planets that have been darkly imaged. And with ALMA, we have observed the debris disk that is just out there. And we know that this system also has a debris disk, okay? This debris disk is very faint and had been basically marginally detected and imaged by ALMA. This is what you see in this image that looks blobby because it's very noisy. But if we were to look at this system with higher resolution and sensitivity, perhaps we could see kind of gaps. This is caused by resonances with this planet B over here. But this is something that we cannot do at the moment, but we might be able to do in the future. And it's the obvious system where to try to do this. Then we have the case of Fomalhaut, which has been imaged at multiple wavelengths, for example, with HST in the optical or with ALMA at millimeter wavelengths. And what has been found is that in this ALMA image that you see here is that this ring is seen kind of eccentric, okay, is inclined to us, but the eccentricity that we see is not just due to the inclination, because if you actually measure where the center of this ellipse is, it's offset from the star, okay, and this offset is significant. It can be measured with great accuracy. So this offset indicates that this ring, if we were to look at it from basically a face-on view, just from above, it would be an ellipse, okay? It's not a circle. And this kind of offset actually matches very well with what has been proposed by other authors, as I showed you in the previous slide. And actually, we can do almost a one-to-one match with some of the simulations done by Nesvold et al. And in this case, to explain an offset like the one we see here, and in the simulation shown here, we would need a planet more or less on an eccentric orbit like this one, okay? So Fomalhaut is a clear example where we see some structure that indicates the presence of a planet on an eccentric orbit that has shaped the distribution of the disk. Okay. Sadly, we haven't found that planet yet, but perhaps with JWST, that hopefully will be launched this year, or with future instruments, we could detect that planet and finally basically compare our predictions with the actual planet that is responsible for this structure. Another case is the famous system Beta Big, which has a debris disk as well. And when people in Dent et al. 2014 looked at how it was gas distributed in the system, they found that it looked like it was clumpy, basically located in 2 clumps opposite to each other. Those 2 clumps resembled very well the distribution predicted for material that is trapped in resonance. So perhaps in this system, what we are seeing is evidence of strong resonance trapping, and that can only happen basically when you have a planet that has migrated through a disk of planetesimals. So this is another case that could perhaps indicate the presence of a planet. And not just that, but also tell us about the migration history of that planet in the past. Okay, so those were 3 examples, but in reality, we have imaged tens of disks. This is a gallery of ALMA images obtained over multiple years, and also as part of a recent survey that has been led by Luca Matra that we called Recents. And you can see that There is actually a variety of structures. This is the case of Fomalhaut I showed you before. There's eccentric, but also there are other disks that seem to be wide and kind of maybe with gaps. Other disks that are simply narrow and circular, and so on. So from ALMA, we have started to look in more detail to the structure of many disks. And the first thing that I would like to emphasize is what we have learned from the radial structure of disks. Okay, so I'm going to be focusing on the radial aspect of disks. So thanks to ALMA, we have started the first large census of debris disk sizes. And from this, we have started to learn how the disk radius, right, correlates with other properties from the systems. We have found that it seems that disks tend to be larger around stars that are more luminous or more massive, right? So while there is a big dispersion here, we have found that there is a trend that small disks tend to be found on less luminous stars, and large disks tend to be found around more luminous stars. The points in this plot represent the radius of disk, and the error bar is not the uncertainty actually on the measurement, but it's the width of disks. So some disks like this one seem to be very wide, while some other disks like the one over here seem to be very narrow. Here the Kuiper belt is shown as a comparison, which is relatively narrow and small compared to disks that we generally find. Not just that, we have also started to look at what is the width of disks, or more precisely, the fractional width. So this is the width of a disk divided by the central radius of the disk. So it's a measure of the kind of proportionally how wide or narrow a disk is. What we have found is that most disks are actually not narrow as the one shown here, like Fomalhaut or HR 4796. Narrow disks are very rare. Most disks tend to be very wide, actually, like the ones over here and beta peak. So beta peak is a good example of a wide disk. Most disks are actually much wider than the Kuiper belt. Okay, and this is very interesting because when we look at protoplanetary disks and the rings that we are finding in protoplanetary disks, like the ones in the D-sharp survey, those rings, if we put them in this plot, are much narrower than exoKuiper belts. And this is, in a way, interesting because we think that the rings in debris disks, or disks in the debris disks, right, indicate the presence of planetesimals, and those planetesimals must form in protoplanetary disks. And we think those planetesimals could be forming in the rings in protoplanetary disks. So naively, we would think that, therefore, these rings of planetesimals should be as narrow as disks in protoplanetary disks. Well, the answer is no. This is what we're finding. And the reason for that, we don't know yet. Okay, so there are many possibilities. One possibility is that these wide disks that we see here actually might not be a single belt or disk, but it's a disk that is divided in two belts that are much narrower. So to understand better this question about the width of debris disks, or what's hidden in these wide belts, I've looked at 3 specific systems with ALMA that we knew they have wide debris disks, and we looked at them with enough resolution to resolve the radial distribution with a few resolution elements. So we will be sensitive to structure in those belts. And what we found is the following. So these are 3 systems around solar type stars that are 50 to 700 million years old, so young systems. And these 3 systems show disks that seem to show annular gaps in the distribution. So the disks are almost like divided in two, inner and outer component. And perhaps it's difficult to see from these images, but if you do a radial cut and some azimuthal averaging, you can recover the radial profile with a high sensitivity. And as you can see, the distribution is almost like broken by gaps in the three systems. And not only the systems show this kind of structure, another two have shown the same. And together with those, it seems to be growing evidence that this type of structure of gaps could be common among the white gray belts. And if this is the case, the white belts that I showed you before in the distribution of widths, right, perhaps are composed of multiple narrow belts, and therefore perhaps there is actually a match with the structure we see in protoplanetary disk, but we don't know that yet, okay? Why this kind of gaps is also interesting is because they could actually be produced by planets. So a planet that has formed embedded in a planetesimal belt, we expect that it should carve an actual gap in that belt, as this movie is showing. So the gap in that belt, okay, the size of that gap, the width, will be directly related to the mass of that planet. And the center of the gap will tell us where is the orbit of that planet. So if we use the information from the observations and try to infer what kind of planet could have produced the gaps that we have found, what we find is the following. Those planets should have a mass that is within these ranges and at distances from the star that are shown by these dots. So if truly carved by planets in situ, those planets would be Neptune analogues, more or less. Okay, with masses ranging between Neptune and Saturn, perhaps. So we are starting to probe perhaps this region finally through the British observations. Hopefully, such planets could be confirmed and detected with upcoming instruments like JWST and the ELTs in the coming decade. So the other kind of disk structure I want to discuss is the vertical structure. So for a system that is very inclined to us, okay, we call it edge on. So we see it like the edge. They're not very good to understand the radial structure they have because all the emission coming from different radii is a bit mixed up. But they're actually very good to understand the vertical structure they have. A clear example of that is Beta Peak, which has an inner disk that seems to be warped or tilted compared to the outer disk. So in this figure that you see here, if it was just a simple normal system, you should see just a simple like red line over here that represents the orbital plane of the system. But we see that the inner regions seem to be tilted or warped. We know that this system actually has a planet close to the star, and that planet, if was initially tilted with respect to the disk, could actually be causing this warp. This is well understood through the theory of secular interactions. And through this kind of interactions, we know that a system, after a few secular timescales, will tend to realign to the orbit of the planet, okay? While doing so, the inclinations of particles in that disk will be forced to higher values that are actually twice the initial misalignment between the planet and the disk, but the average inclination of particles in the disk will be equal to the inclination of the planet. So the whole disk will realign to the orbit of the planet, but it will remain puffed. Okay. The problem here is that actually this kind of interactions predict that the whole disk should realign to the orbit of the planet in a timescale that is shorter than the age of this system. So why do we see that this system is warped or still like misaligned, especially the outer regions compared to the inner regions? The answer to that could be that perhaps there is a second planet in this system. And as I told you before, in beta peak, we see these clumps in the gas distribution, and that could be evidence perhaps of a planet further out that has trapped planetesimals, right? So perhaps it's that extra planet further out that is on a slightly different orbit compared to the planet closer in, and therefore both planets together could be warping the particles in this system. So the debris disk warp could be perhaps explained by a misalignment between the inner and outer planet. And this diagram over here basically shows what we think the orbit of the inner planet is and how it compares to the outer disk. Okay. So beta peak is not only interesting because of the warp. It has also been shown that this system has a hot and cold dynamical populations of inclinations. The evidence for this comes from the vertical distribution of the disk. So if we make a cut along the y-axis in this system, we can see that the vertical distribution, shown as this purple thick line, can be not well fit by the dashed red line, which is the best Gaussian fit. It has a stronger peak and stronger wings, okay? And this fact means that because for a single population of inclinations, we expect a Gaussian distribution, this means that this system seems to have a double populations, or at least a double population of inclinations, with a population having very low inclinations, so very peaky here distribution, and a population having higher inclinations, reaching higher heights. This can be shown better when we see the distribution of inclinations in the system. So the blue line shows the best fit model for beta peak, and you can see that there is a strong peak for low inclinations. So this is a population that dominates the emission and creates this strong spike in the midplane of the disk. And then we have another extra population with higher inclinations, okay, and that recreates very well the wings in this system. This binomial population is not new. It's something that is found in the Kuiper belt, okay, seen as green or red curves. We have like a peak for low inclinations, and then an extended component and a second peak in higher inclinations. And this kind of bimodal population has to do with the evolution of a system, with how inclinations are excited. In the case of the Kuiper belt, it has to do with Neptune and how it has migrated, trapped particles in resonances, scattered material, and so on. So the fact that we see it in Kuiper belt is telling us that there seems to be interaction with a planet, and that planet is potentially and very possibly the same planet that has created the clumps that I've told you about and the warp. So the next topic, final topic I want to discuss today is gas in the ray disks. And I think it's a good idea to start by discussing how are we detecting this gas, okay? So there are basically two main methods to detect this gas. The first one is to detect by looking at emission lines from a system. So if we point a telescope basically to a given system, and then we integrate all the emission we receive from it, we might see some emission lines at particular frequencies. So gas emits radiation, right, at specific frequencies. And typically for disks that are cold, far from the star, that emission will be mostly at far infrared and millimeter wavelengths. So those are the typical wavelengths where we expect to find these emission lines for typical cold disks. We can also for specific kind of systems that are inclined to the line of sight, we may be able to detect absorption lines. This happens when light from the star travels towards the telescope, and in between doing so, it goes through the disk. So when going through the disk, some of that emission from the star will be absorbed by the gas, again at specific frequencies. And we can search for this kind of absorption in disks that we know are close to edge on. And then we can look for this kind of absorption and learn something about the gases. So there are these two different methods which are complementary, and we can learn basically different things by using them. The first method I would like to discuss is the gas CNN absorption. We know this gas exists around systems since basically 75 decades ago, when it was realized that beta peak showed absorption features from calcium gas. This figure is from Ferlet et al. 1987, where what you're seeing here is the stellar spectrum as obtained from a telescope. So if there wasn't any gas around, we would expect to see a spectrum following this orange line, okay? And the shape here of the spectrum is because of calcium that is present in the stellar atmosphere, and this white line, absorption line in the spectrum, is due to the rotation of the star. Okay, so this stellar absorption over here is due to gas that is far from the star, that is rotating very slowly. Okay, otherwise we would see a white line, and is centered at the same velocity as the star. So this means that this gas is orbiting the star without any radial component. And on top of this, we see other components that are red-shifted and that vary with time. Okay, so this is a variable absorption component. Ferlet et al. At that time interpreted this component, as this variable component, as evidence for star grazer objects or falling evaporating bodies, basically exocomets, which are on eccentric orbits and are sublimating due to the high temperatures that they reach when they get closer and closer to the star. The reason why here they were seen to be redshifted can be understood if we look at this very basic diagram where we have a star, a comet on an eccentric orbit, and this comet, in this case, is moving with this velocity here, shown by this vector in red. So as you can see, if we were to observe this system with a telescope around here, we'll see the light from the star going towards the telescope, but being absorbed by this comet over here that is moving away from us. And therefore, the emission that the telescope will detect will be absorbed by the gas from this comet. And because the comet is moving away from us, we will see that absorption to be redshifted. So in this case, the absorption from the gas over here seems to be coming or originating from material that is going towards the star. Okay, it still hasn't reached the pericenter. So decades later, we know about 30 systems with debris disks that are highly inclined or without debris disks that show this kind of absorption. And not just that, we also have monitored this kind of absorption and seen it evolve, okay, in time. So this figure over here from Kennedy 2018 shows in the x-axis we have radial velocity, so wavelength, and the y-axis we have time, and the colors represent the strength of the absorption. So we see that there are some features like this one here or here that are stable in time, they form vertical lines, but other features like the one over here seem to evolve in time. So it's changing velocity. So it's changing radial velocity, and that means that it's accelerating, okay? And these kind of things that we interpret as comets is also supported by the fact that in a few systems, that have been monitored, for example, with Kepler, with the Kepler mission, it has been found that there are transits that seem to be asymmetric, so not like the transits we expect for a planet. And those transits that are asymmetric were actually predicted in 1999 by Le Cavalier et al. So they predicted that if there was something like a comet transiting in front of the star, we should see a sharp drop in the flux of the star, and then a very smooth transition and going back to the normal stellar flux. Okay, so these two kind of lines of evidence really supports the idea that the absorptions that we see are caused by exocomets, basically things on eccentric orbits rich in volatiles, or simply going close enough to the star to start sublimating even the rock, like rocky material. And then we have gas in emission. Okay, so gas in emission was detected like 25 years ago or even more, when looking for CO gas in young systems. So this figure over here shows the infrared axis, okay, the fractional luminosity of systems as a function of the start temperature of the star. And this line over here that you see here divides more or less, it's a rough divide between things that we think are protoplanetary disks and things that should be debris disk. Okay, so the black dots show systems that show a CO detection. So most of protoplanetary disks were known to have CO gas as expected, but some debris disks, in this case 49 Ceti, showed CO gas. And that was not understood at the time. It wasn't clear where it came from, but some guesses were done, and Zuckerman et al. Suggested that the gas could originate from collisions of icy comets. However, to produce the right amount of CO, you need a very high collisional rate, which was unusual and meant that this scenario wasn't very likely to explain the CO levels seen around 49 Ceti. Decades later, thanks to ALMA, we know there is carbon, oxygen, or CO gas in 20 stars or even more. We have found that 11 of 16 young A stars with bright debris disks have CO gas. So CO gas is something that is very common around the systems with bright debris disks. And with ALMA, we can make images of how the CO is distributed in those systems, like the image over here. And not just that, but also see the kinematics of those systems. Because with ALMA, at each pixel, we get a spectrum, so we can derive what's the radial velocity at that point in space, and produce maps like this one, which we call moment one. So each point in this map is colored according to the velocity. So the red color here means that the gas emission is red shifted, and here is blue shifted. So this part of the disk is moving away from us, and this part is coming towards us. Okay. However, despite many observations, right, the question of the origin of this gas was still open. Is this gas of secondary origin? Is it leftover of the protoplanetary disk? And this was a very big question that we have, and it's still not 100% solved. So for systems with not much gas, this was easy to answer. This is because if CO densities are low enough, we know that it will be destroyed by UV radiation from just an interstellar medium in only about 100 years. Okay, there's nothing to shield the CO from this radiation. So that means that CO needs to be replenished somehow, otherwise we wouldn't see it. How is the CO being replenished? Well, we think the following is happening. We have a planetary system with a star at the center, perhaps some planets, and then a planetesimal belt, right? And those planetesimal belts are colliding, right, and producing the dust we see. But those collisions perhaps also release some gas that is trapped inside them. If this happens, we will expect that the gas and dust should be collocated, and in fact, this is the case for one system, for example, HD 181327, that we imaged with ALMA. And we see that the gas, shown here in blue, this is a radial profile of where the gas is seen, peaks at about a distance from the star, very similar to where the dust peaks. So this kind of scenario or hypothesis works actually very well to explain a system like this one, which doesn't have much gas. Now for those kind of systems, we can go one step further. So we expect that the CO in this system should be close to steady state, and that means that the rate at which CO is being produced, here represented by m dot plus, should be equal to the destruction rate, here represented as m dot minus. The rate at which CO is being produced is equal to the rate at which the belt is losing mass, so how fast planetesimals are colliding, how frequent they are losing mass, times how much mass in CO is inside the planetesimals. And that must be equal to the rate at which CO is being destroyed. And that's equal to the mass of CO gas that is in the belt divided by the timescale at which is being destroyed. Okay. FCO could be guessed from solar system comets, which have FCO values that range between 2 and 20%. M dot is how fast planetesimals dust are destroyed, right? And this can be guessed by how much dust we observe and how it is distributed. The mass, the CO gas mass, can be directly constrained from the observations. And finally, the CO lifetime can be constrained by the intrinsic properties of CO of the molecule. So based on this, actually, because we can constrain m dot, mco, and tau CO, we can actually derive how much CO there is inside planetesimals. And what we have found so far is that that value is consistent in extrasolar systems and solar system comets. So this figure shows the x-axis, different systems and different comets. On the y-axis, you see this fraction of CO. So the blue bars basically, although very uncertain, are consistent with the values found in solar system comets. So this is a good check, first of all, but also seems to suggest that there could be similarities between exocomets and solar system comets. But that's the story for the systems with not much CO gas. In reality, we find that if we look at the mass distribution, the CO mass distribution as a function of age, we see that protoplanetary disks have high CO levels, and debris disks, some seem to have high CO levels and some low CO levels. These ones over here require CO mass fractions that are consistent with solar systems, but these ones over here would require very, very high CO mass fractions, which wouldn't be possible. So how come we have CO in these cases? We didn't understand very well this case. Until very recently, we thought that the CO in these systems must have been a leftover from the protoplanetary disks. But very recently, in a work led by Kamta and Kral, we found that actually, if we look at what happens to the products of the CO destruction, that is carbon and oxygen, those things will evolve in time. And actually, the carbon that is being produced due to the fact that CO is being destroyed, if it accumulates enough, it can shield the CO. This movie you see here, it's for a case in which the carbon that is being created from the CO photodissociation doesn't reach the level that is high enough, this dotted line, to shield the CO. So CO here is in steady state, it's being produced and destroyed, and carbon is being produced and forms an accretion rate. So the x-axis is distance from the star, and the y-axis is the surface density. So I'm going to play it once more. So carbon piles up, then grows, and then reaches a steady state. But if the production of CO is a bit higher, then the production of carbon will be also higher, and carbon could reach this critical value at which it can shield CO. And when that happens, I will play it again. CO becomes shielded and can grow, the surface density of CO can grow to very high values. Okay? And that is like the key to understand why some systems can have so much CO. This means that the observed gas in all systems with debris disk could be released by volatile-rich planetesimals. But that's not the whole story yet, because CO cannot be released at a high rate for too long, and this is because there is a collisional evolution going on. So CO, the release of CO depends on the mass of a belt, and the belt mass decreases with time due to collisional evolution. So this is total mass in solids for a belt is a function of time for different initial masses. So for example, the red curve is for a case of a disk starting with a very high mass. And that disk will evolve with time, will evolve very quickly, and actually will converge to levels that are consistent with a belt that started with a lower mass. So no matter how much mass you start with in a belt, you will converge always to basically the same point in the future. So that means that you cannot stay producing CO at a high rate forever. You at some point will have to decay. So let's see again what happens to the evolution when the CO production rate drops with time. So carbon is accumulating, right? Then reaches the critical threshold, CO suddenly is shielded and can go up, but then the production rate of CO drops and the CO levels drop as well. I'm gonna play it one more time. So you can see the CO surface density goes up and then it goes down. Okay. So that means that we need to take this into account if we want to model the gas evolution of debris disks. And the best way to do this is to approach the problem from a population synthesis perspective. So this means that we will model the observations not one by one, but just as a distribution. And this has been done from decades ago when looking at the dust. So these figures show the 24 micron axis for different systems as a function of their ages. Those are the big dots. And the small dots represent a synthetic population, so a model producing random systems with different initial masses, different radii. And those models were able to reproduce very well the dust evolution. Okay, so those models constrain very well how M and the evolution of M, the dust mass or the belt mass, evolves. So we can take the information from those models and use it as an input to model the gas. So if we do that, and we simulate thousands and thousands of systems, what we find is the following. This figure over here shows the mass, the CO mass in a given system in log scale as a function of age, where the color is the radius of that belt, that planetesimal belt in that system. And this is for a whole population, a complete population, but observations usually have biases. So we do surveys, but we focus on a specific type of stars. So if we compare the model using the same biases, basically only simulated systems that we would have observed, then we can compare the distribution of those systems that are kind of as biased as the observations to the observations. And this is what the contrasts show here. They show the model distribution And in red, you see the observations. So each point here is a different system for which we have measured the CO gas mass, and the blue shows the model distribution. And there is a very good match actually between the two, given all the simplifications in the model. And this means that this model of secondary origin for the gas, by that I mean that the gas is being produced by collisions of volatile rich material, so exocomets, is able to reproduce very well the observations. And therefore, there's a lot of evidence towards thinking that the planetesimals that we see in debris disks should be volatile rich and similar to solar system comets or Kuiper belt objects. So what are the consequences of this gas? Well, I think there are two main important consequences to consider. One is that because gas is being released and it should spread due to viscosity, gas that is released in the outer regions will reach the inner regions, and while doing so, it might encounter some planets. Those planets might be able to accrete some of that gas, and this is what has been studied by Kral et al. 2020, where we see how much gas in the atmosphere of a planet as a function of time, as it accretes this gas that is being released at a large radius. So what Kral et al. Found is that an Earth mass core could actually accrete enough exocometary gas to form an atmosphere as massive as the Earth's one, or even greater. And this is important because a planet like the Earth might be born volatile poor, as we think Earth did. So the delivery of volatiles might be something that is necessary for the emergence of life. The other big kind of consequence that that gas has for planetary systems is that the presence of this variable absorption seen in some of the systems, right, is evidence for bodies in exocometary kind of orbits, in cometary orbits, things that are formed a large radius that are scattered by planets perhaps, and then they can reach the very inner regions. So those bodies, if they collide with a planet, let's say at 1 AU, they could deliver a lot of volatiles, but also they could erode those atmospheres. So in this figure by Wyatt et al. 2020, you can see for planets of a given radius and orbital period or semi-major axis, are they more likely to basically accrete material that from impactors, or are they more likely to have their atmospheres eroded due to those impacts? So in brown, you see those systems that would lose atmosphere mass in brown, right? And in green, you see systems which would have their atmospheres growing. So either impacts of volatile rich material or just accretion of the exocometary gas could have strong consequences for the evolution of planetary systems. So with that, I would like to finish and leave you with some stay-home messages. So I hope I've convinced you that debris disks offer a complementary view of planetary systems. Debris disks can have a rich radial structure, gaps could be common, and perhaps they are caused by Neptune analogues. The complex vertical structure of some disks seem to indicate that there are distinct dynamical populations and misalignments. We have also found that mature planetary systems are not gas-free. Gas can be used to infer the volatile composition of planetesimals. That gas should spread and could be reaccreted by planets, perhaps leading to volatile delivery. And finally, the bodies in cometary orbits that reach the inner regions could also impact on planets close to the star and perhaps deliver some of their volatiles. And with that, I would like to finish. I hope you stay safe